All right, let's get started. First thing, actually before the initial task, a request. So currently my little camera's set up so that I can just post the class to Google Classroom for when people miss. They can hop on there and see what we talked about and all that good stuff. The mic is attached to me, so it's not actually going to be picking you guys up very much at all. It's right on my chest, so it should only be hearing me and probably the clicking when I write on the board. But when we're going over stuff, if you need to get up and go get a tissue or go to the trash can, do me a favor and try to walk around table 2 so I don't have to try to edit you out of walking in front of the camera. That would be appreciated. Aside from that, then we should be good. Any questions there? All right. Then, starting with our initial task, if Mr. Hawkins, hi, that's me, dropped a tennis ball, would it speed up, slow down, or travel at a constant rate or velocity? Today will be a decent day to get some extra credit points, as always. What do we think? What you think, Lexi? Would it be constant? I don't know. You think it's constant? Okay. Sam, what do you think?
Speed up initially to terminal velocity, and then speed up then you get that constant form to stay there.
I don't know. Would it?
Yes.
Okay, that's what Sam thinks. What do you think, CJ?
Wouldn't it be constant because you're like alternate, you're not throwing, so like it wouldn't like go fast and then slow down. It like say the constant because you just alternate.
Okay. Still got a wood in it in there, so I think that's what CJ thinks. I don't know, though. Paisley?
It would speed up as it slows down because more gravity would get hold.
All right, out of those, I'm more inclined to trust that answer simply because she just said, matter-of-factly, it would speed up. Didn't form it as a question. I'm just giving you guys a hard time. You're fine. So we got stay at a constant rate. CJ, you said constant rate. Sam said speed up to a point and then constant. And yours was speed up. Did you also say to a certain point?
No, I just said it would speed up.
Okay.
Like farther down that hill.
All right, so let's test. Now, my eyes are not the best. That's why I got to wear glasses. So, to be honest, I can't tell, but maybe some of you can. Here's the ball. It fell. Did it look like it sped up or was going constant? What constant? It's really hard to tell. Some people in first period were saying that they could tell that it was speeding up. I don't know if that was just in their head or not. But what's up, Isaiah?
It would be speeding up because it's going from 0 to moving, so it wouldn't be speeding up even if it was just some small amount that we can't see. If you drop the ball from infinite height, you'd be able to clearly see once you're hitting the ball.
Oh yeah, because
Alright.
like if they think about like an
Yeah.
asteroid in the atmosphere, it speeds up as it goes down through the atmosphere, and like it's actually speed up because it develops the fire.
Okay, so we got 2 points there. Isaiah said, well, it had to have been speeding up at some point because all I did was let go. I didn't throw it up or down. I just let go. And if it was truly going at a constant the entire time, I guess it would just float there, which I wish I could do for an example, but I can't. So we know it had to speed up to some degree. And then Paisley mentioned, you say asteroids?
Yeah.
Asteroids, they're going at a relatively constant rate while they're in space, but as they get closer and closer to Earth, they start speeding up so much to the point where they oftentimes will burst into fire as they're coming into the atmosphere because they're going so fast and suddenly interacting with a bunch of friction. So they heat up and usually break apart and don't cause any real damage. But our basic human eyes are not very good at tracking minute differences in speed of moving objects. So we oftentimes have to rely on more thought out experiments, one of which, like what we did yesterday with Timmy and those other discs, we had Timmy up here, and I think it was fairly clear that Timmy started out really slow and then steadily got faster and faster, which if you're going down a ramp, you're essentially falling, you're just falling at a less of a steep angle. So Timmy was speeding up, he was going faster, but it did seem like he was going faster and then got to a certain point where he just kind of stayed constant. That's what a lot of your data suggested too. Like those last two data points, almost everyone had the same velocity for the last two data points, because it seemed like your disk hit its, I guess we could say, kind of a terminal velocity, which terminal velocity, we may mention that more in the future, but that's just something will speed up to a certain point until the air resistance kind of just counteracts gravity, so it doesn't keep speeding up forever. Like squirrels, you can take a squirrel and chuck it off the Empire State Building, and it'll be fine because it hits terminal velocity almost instantly, so it'll just glide down to safety. I don't recommend doing that because it would probably still be terrifying and rude, but you could, and it would be okay. Moving on from there. There's your daily animal abuse. But back to our Timmy lab. We looked at one graph for position versus time, talking about our little constant velocity cars, and we got a line, a straight line, indicating it's going at a constant rate. But yesterday, I got you all to input your data into a Google Sheets form, mostly so I could steal it and make my own chart, which is what I have here. This is all of your data grouped together. And then I plotted the line to get this nice little curve to it. But that curve indicates that that's different from what's going on over here. Because we know if it's going at a constant rate, we'd have a straight line. That is definitely not a straight line. So there must be something else involved, which we'll get into with chapter 4, all about acceleration. That's the main subject for chapter 4. It does still just take chapter 3 and add stuff onto it though. So I wouldn't lose my chapter 3 notes, but I would start a new section and title it chapter 4, Acceleration. So if you haven't already gotten your notes out, do that real quick while you file away your initial task. Oh, I need to jot down points. I think that was everybody. And at this point, I guess I'll flip the sign around just to make sure that our phones are put away for the next little bit. Except mine, it's there. I won't look at it though. But before we get into chapter 4, we do have some of the chapter 3 exam statistics. I apologize, I did not get all of them graded last night. I couldn't do it because the first 2 classes I graded did not turn out the way that I was hoping or expected, and I had to take a break. So let's get into that. First period, first thing I always look at after I grade the papers and put them in PowerSchool, I want to know what the highest grade was. And their highest was 100%. So that's good at least. That tells me that my test is possible, all of the questions are solvable, and that my answer key is correct because somebody agreed with me. So that's a decent indication that it's right, that it works. It's also the same answer key I've been using for 5 years, so hopefully it's right. But then from that, I look at the average because it's always good to know the average. That one didn't turn out so great. So somebody in the class did really well, but overall, not so good. And I thought, okay, averages, when I'm looking at grades, that's not the most useful statistic for me at least, because averages can be skewed by extremes. Like I had this guy get a 100, that's going to skew it towards the positive, but I also had this other dude that got, I think, a 10. So that skews it in the other direction pretty badly. So more important than averages are medians to me when it comes to grades, because that tells me how half the class is doing versus the other half. So I looked at that, and it wasn't much better. But that does tell me perfectly that half the class passed, half the class failed, which is certainly not my goal or what I'm shooting for exams. Think we can generally do better, and I have a few ideas on why it may have been so bad. But I didn't want to dawn on it too much. I thought first period physics, that's really early to be doing physics. Maybe they're unique. So then I looked at second period. Their highest was 75. Not great. Possibly the highest score I've ever put on the screen up here. I'm not sure. Their average was also slightly worse. Their median was a little bit better, though, so that's one silver lining, I guess. Not much better, but a little bit better. But at that point, I don't know the rest quite yet. I had to take a break after those first two, and I'll get the rest graded and get the rest of the statistics today. But already figured out this, and also I did my little survey after the test with all the classes. I think, did I do that with you guys? Ask you what you think you made, thumbs up and everything? Okay, which you all were the most confident, but even with that, there was a decent chunk of us that were not so confident. So I'm hopeful that our scores are better than those two, but I'm not convinced quite yet. I'll get them soon. All that being said, there is a kind of exam recovery in my class. So tomorrow you'll get your actual exams back. And then from there, you can make corrections and are encouraged to do so because, like I've mentioned, Chapter 3 is not going to go away. So you really need to figure out what went wrong and try to figure out and get that stuff fixed before we get too far into Chapter 4, because it all builds on top of each other, or itself, rather. So you'll redo questions that you missed points on, and for redos, you have to show your work. And a point about that. On tests, you're not required to show your work. You are strongly encouraged to, though, because I'm a fan of partial credit. So if I'm sitting grading papers, if I see someone tried something, they get a point. They put some math down, they attempted to put something together, so 1 point for trying, well done. If they have the right unit, there's another point. If they tried something and got pretty close, but maybe they made a little mathematical error or missed a negative somewhere and have the right unit, they'd get 3 out of 4 points. And then if they got everything, they get 4 points. But if all you put is a number and that number's not correct, I have to give you 0 out of 4 points because I don't really know how close you were based on your wrong answer. You might have been close, but I can't tell without some work. So you're encouraged to show your work, especially on tests. And in the future, with some of our rigors, our assignments, there will be some questions with stars next to them. If you ever see that, you got to show your work for those questions, at least for a little while, until I'm convinced we're all where we need to be. You'll do that on a separate sheet of paper, staple that to the original and turn it back in. Doing so can get you up to the next letter grade. I'm not going to let corrections get you all the way up to a 100 because I don't want people to stop trying on tests and relying on corrections. But if you failed it, that can get you up to a 70. If you made a D, that can get you up to a C, and so on. If you already have an A, corrections won't really actually do anything for you. I'm sorry. Questions there? All right. Once you get those back, you'll get those back tomorrow. Corrections will be due next Wednesday so that we can get those in and get that stuff fixed before we get too far into Chapter 4. That's the goal, at least. But also, I'm hopeful that this group, I'll have a much easier time grading. Because that's the other reason that I had to take a break, because it takes forever to grade really bad assignments. People that get everything right, those are really easy to grade. You just fly right through them. So hopefully that's what I'll have for this group. But now on to our little chart of where we are. We've made some progress. We're here, getting into acceleration, but you'll notice that from here, it starts creeping up in difficulty. And that's because, like I've said, everything just stacks on to the chapter before it. Except for here, it does get easy for a little while once we get into forces because we're just doing basic addition and subtraction for a few days. But for the most part, the math, the algebra does get a little chunkier, I'll say. Just, we got to do a little bit more from time to time. Speaking of, is there anyone that still needs to take that exam from Tuesday that's in here right now? Okay, great. Then there was a few questions I wanted us to run through just to make sure we have those. These 3 questions, if you can do those, you follow along, then I think you're okay to start venturing into Chapter 4. I would say these are the most important 3 questions from the test. It's also why I made them the first 3 questions of the test. Starting with, is it possible to describe a situation in which someone moves a non-zero distance, meaning to have non-zero distance, if I start here, I have to go somewhere, I have to move, but they have a displacement of 0. Paisley, what do you think? They go in a circle. So if I walk over here, and I'm actually not going to walk around a circle, but if I walked in a circle and got back to where I started from, then my displacement would be 0 because I started and stopped at the same point, but I did move, so I do have some distance. What's up? There's another one. Go 50 forward, go 50 back, or negative 50, back to 0. I moved a total of 100 meters, but displacement-wise, I'm still in one spot. That's the difference between the two, and we really got to know that difference going forward. Displacement just cares about your initial point and your final point. It doesn't really care about the middle ground like distance does. To be fair, though, first and second period, most people got that answer somewhat right. Everyone said yes. Some people gave me examples that didn't quite work, but everyone was like, yeah, that's possible. The second one, though, that got a little stranger. Is it possible to describe a situation in which someone moves 0 distance, meaning, okay, I start here, and I'm not allowed to move, because if I go anywhere, I've moved some amount of distance, but have a displacement above 0. Is that possible? Abby? No. Simple answer, no. No. You got credit for that question because it's just simply not possible. I cannot move from my initial position without moving. Is essentially what that's asking me to do. I guess you could maybe make an argument for teleportation, but as far as I'm aware, teleportation doesn't actually exist. And even if it did, I would still argue that that is moving distance. So I don't think that would work either. So that one's not possible. The next one, the one that I think is probably the most important, is being able to solve mathematical questions like this. Let's run through it. And I think, my theory at least, or why I had so many issues here, might just be because I used giant numbers and that threw some people off. But that's not necessarily going to stop on tests, because if you can solve a question that's 2 digits, you should be able to solve that same kind of mathematical question if there's 15 digits, because the math is all the same, it's just a few more numbers to write. Let's see. Superman flew 500,000 meters due west, which west is generally considered our negative direction. I'm going to go ahead and make a note for myself, that's negative. Then 25,000 meters due east, that's our positive. What's his total distance? Let's hear from Sam. What do I do? 525,000, so I'm guessing you just added those together. All right, 525,000. If that was on your test, you get 3 out of 4 points. Meters. And there we go. Now, if I wanted to show my work, I guess just 500,000 plus 25,000. And there we're set. Distance does not care about the direction. It just says all of your movement added up. Most people got that one. I had a lot of people forget their units, but aside from that, we were mostly good. The displacement, though, that's where things started to go south. Displacement, we do need to keep track of those negatives. So how am I going to solve for displacement? Kerrigan? Negative 500,000 plus 25,000, giving me 4. This is just an example. I heard you. If you wrote this on your board or on your paper, I would look at that and I can see what you meant to do. And then I see that you got the wrong answer. So I'd give you 3 out of 4 points. Because I know you knew what you were doing, but maybe you just clicked the wrong button in your calculator, because there should be a 5 there, so let me fix that. There we go. That negative lets us know it's in the negative direction. I did have a few people that instead of putting the negative, they just wrote 475,000 west, which that works too. That is perfectly fine. I would maybe encourage people to get more used to writing the negatives just because the negatives will factor into our calculations further. Like if I have to use this number later for a calculation, I'm going to want to keep in mind that it is a negative. But for your final answer, you could just put west, I suppose. Then to C, here's where things really went wild. If Superman took 0.0065 seconds to complete the trip, what was his average speed? Hopefully we all have this equation memorized already. Distance over time. So I'll grab my distance from part A, 525,000, divided by that tiny amount of time. And then throw that into a calculator to get an even more giant number. 8076923.77. Then what am I missing? Emma, meters per second. Now I can give Emma a point for it. Which I'll do right now because there's a few other points I need to write down before I forget. So we got our number, we got our units, and I think my TA might need to turn his music down a tiny bit. Definitely, he's going deaf over there. You got a good taste in music, but a few of us can hear it. Turn it down a little bit. Then last one for our velocity. What was his average velocity over that same amount of time? Almost the exact same setup, but we need our displacement instead of distance. So I'll grab my answer from part B, 475,000 over that time. Negative 7307692.08 meters per second. And there we go. Turns out Superman is kind of fast, which I guess checks out with comic books and stuff. Questions there? Once again, I feel like we're fairly confident, but what's up?
So with that one, I didn't make it where West was negative
Mhm.
because I thought it kind of mattered on which way you were looking at Superman activity because West could be your negative, but if you're on the opposite side, East could have been your negative. I got those answers. It's just I didn't have the negative signs for either D or B.
Okay, so if that's the case, you probably are going to end up getting 3 out of the 4 points there. And for everyone going forward, our standard, meaning the human science standard, is that East is positive, West is negative. But you could make a case and say that I don't want West to be negative for this question. I would rather West be the positive direction, East be negative. You're actually allowed to do that. But if you do, you just need to make a little note on the question. Say East negative, West positive. Then you can make West positive if you want and East negative. As long as you're consistent with it, then the answers will be fine and everything will turn out still correct. We're good there. They are just directions. They're kind of arbitrary, but unless it's stated specifically by you or by the question, the assumption is that it's the general compass rose situation. Any other questions? All right. And I'm going to leave the rest. If you get your paper back tomorrow and it's not so great and you were expecting better, then hopefully you'll do those corrections and you're welcome to ask questions about them if need be. But we're going to move on to chapter 4 in just a second. What's up?
I was wondering, you did have two tests, right? Like they do two different ones. How did they first start?
All right, everyone's taken the test already, so I'll let you in on a secret. The difference is one of them says A on it and the other one said B on it. That was the only difference. But sometimes I do make differences, but on the first one I was like, I don't want to make 2 different keys. I'll just change the title. That'll be enough. All right, on to chapter 4. So step 1, we've got 3 main objectives. The first one we can maybe already do, define and describe acceleration. Can anyone already do that for us? Basil? Picking up speed as you go. That covers about half of the situation. Jackson? How much time and speed it takes to get to terminal velocity. You're kind of dancing around almost the equation there, but I think we're missing a little bit. Isaiah? An increasing speed over time. That one, again, we're almost nailing down the definition, but that also covers half the situation. Let's hear from Lily. Having an increasing velocity. Again, that mostly works. That covers half the situation. And CJ?
Like increasing the speed but having the same amount of time.
Increasing the speed but having the same amount of time. Not sure what you mean. Fair enough. Touche. Anyone want to add anything? Tristan? Doesn't have to be. We can accelerate slowly like Timmy, or you can pull out onto the highway and floor it so you don't get rear-ended by oncoming traffic. All right, we'll leave it there and we'll get a more solid definition in just a moment. But all good starts. Second thing, describe and analyze motion in one dimension using equations for acceleration. We will get an equation. We'll actually get one in a few minutes. But we will start out keeping things simple, assuming everything just goes right or left. But eventually we'll add in that second dimension up and down. We'll even have a few questions that can go right, left, up, down, forward, backwards, incorporate all 3 dimensions. But we won't actually do those too often. Then last one, determine acceleration from the slope of a velocity versus time graph, which is essentially what we did when we determined velocity from a position versus time graph. If we do the same thing, but instead of plotting position, we plot velocity, that slope will give us the acceleration, as we'll see, with a lab that we'll do somewhat soon, I think. 2 weeks, we'll be dropping fireballs through lasers. Sounds way cooler than it is, because you can't actually see the lasers, and the fireballs are candy, not actual fireballs, but it's still fun. But now on to some terms. 2 terms, well, 1 term we definitely already know, velocity. That's how much your position is changing as time goes on, or you could describe it as your speed and in what direction you're traveling. Now for acceleration, could be speeding up. That's everyone's general understanding of acceleration. When I turn out onto the highway, when I leave school, I do hit the gas pretty hard most of the time so I don't get rear-ended, and I accelerate fairly quickly until I get to about 60 miles per hour, and then we'll say that's as high as I go. But acceleration really is just changing velocity. And we'll actually see in just a moment an example of it doesn't always mean you're speeding up. It could mean you're slowing down. It all comes into being a rate of change. Both of these are rates of change, but I wanted to make sure we understood the term rate of change first. So we'll give someone another chance for a point. Can someone describe to us what a rate of change is, what that means? Jeremy, or Jeremiah, rather. Slope on a 2D graph. It is sometimes. If your x-axis is time, I would agree with you. But that x-axis being time is really the key factor there. The rate of change is something changing as time goes on, which is the case for a lot of graphs that you've probably seen before. We'll deal with a lot of rates of change, and probably the most important rate of change you will experience in your life is your bank account. That's one that I care a lot about. I always want my bank account to have a positive rate of change, and for the most part, it does. I'm pretty good with money. I'm fairly frugal. It usually has a small increasing rate of change, although last summer I did buy myself a gaming PC for the first time in my life, so for 1 month I did have a pretty steep negative rate of change on that bank account number, which was a little sad. Your age, that's also a rate of change. It keeps going up as time goes on. Any other obvious rates of change? Hair length. Hair length is also a rate of change. Increases as time goes on, and sometimes shortens as time goes on. If you're in the middle of a haircut, as time goes on, your hair gets shorter. But we'll talk about many more, but sticking with velocity and acceleration for now. To get into acceleration, have a little mental experiment for us using these 4 little pictures. First, does anyone drive a truck in here? Specifically, does anyone drive like a crappy truck? All right, no? Well, good on you, I suppose. When I was in high school, I did not have my own car, but my brother let me drive his truck to and from school for about half the semester or half the year. And it was very old. It was giant, bright blue Ford pickup truck. I don't know how old it was, but definitely way older than me. And it had some issues. It was stick shift and everything. I hated it. One issue it had was, this is kind of a made up story a little bit, this part. It didn't actually have an oil problem, but let's pretend my old pickup truck had an issue with its oil in that it was just leaking oil every single second. A drop of oil came out, hit the road. And let's say, because I'm into weird things like physics, let's say I wanted to do an experiment and track that. I get out of my truck, I look at the road, and the road looks like this. What was my truck doing? I heard someone say it. It stopped, it's standing still. It's in one spot. That oil is dripping and hitting the same spot every single time. So it's not going anywhere. Okay, the next day, I do another experiment, and then I get this. What was my truck doing? All right, I heard a whole lot of things. Someone raise a hand so I can focus on one. Let's hear from Lexi. It's moving at a constant speed. We know it's constant because these dots, these oil droplets, are equally distant apart from each other, or equidistant apart. So the truck is covering the same amount of distance every single second, so we get equal drops. And then, next day, I do another experiment, and I get this. What's that one doing, Giovanni? It's accelerating. What do you mean by that more specifically? Perfect. So not only is it accelerating, it is speeding up in this case. The droplets started out slow and then steadily getting further and further apart as I picked up speed. Maybe I was at a stoplight and it finally turned green, so then I was able to pick up speed and go a little faster and faster. Then what's happening over here? Go with Jeremiah. Slowing down. They were far apart. I was covering a lot of distance, and then steadily, maybe I hit another red light, as is the case around where we live. So I had to come into a stop, slowing down. But there was, I made Giovanni be a little bit more specific because he said accelerating for this one. Jeremiah also could have said accelerating for this one because this is an example of acceleration. Acceleration doesn't actually mean that you have to be speeding up. It only means that you have to be speeding up or slowing down. That's one of those words that in regular day-to-day speech, we've used a word incorrectly for so long that we've almost forgotten what it is supposed to mean. Usually we think acceleration, I'm hitting the gas, I'm speeding up, but it doesn't have to be the case. Just changing velocity, that's acceleration. Also, a few more examples. Like we started with dropping a ball, it'll speed up as it goes down because gravity's pulling it down, making it speed up. We'll get into gravity in a couple chapters. We could go play skee ball and roll a ball up a ramp, and it'll slow down as it goes up the ramp, but it's still accelerating, it's just getting slower. And if you've ever been on a roller coaster, you've experienced lots of acceleration. Even if that roller coaster was going at a constant speed, but it took a turn, turning is a form of acceleration because if I turn, I'm changing my direction. Even if my speedometer stays the same, since the direction changed, the velocity changed, which means my acceleration had to have been present, I guess. It had to have some acceleration to cause that change. Two examples up here. We've got ball 1, ball 2. Their velocities are shown. One of them is accelerating. Which one is it? Go with, I know it. It's there. Cameron. Ball 2. Ball 2, we can see it speeding up. The velocity is increasing, and it's going down a hill. Generally, when things roll down hills, they speed up. I can't write points down with this. So we had Giovanni. Next question, while I write down points, because we all probably agree that ball 2 is the one accelerating. Oop. But what is that acceleration? That'll be my next question once I write these down. All right, the ball's acceleration. What do you think, Sam? I like the number 2. We started at 0, went up to 2. From 2, we went up 2 again. 4, we went up 2 again. But since acceleration is going to be something different from velocity, we are going to get a different unit for it. Do you know what it is? Or do you have a question? No? Okay. We could say it's going in the positive, so we could say the acceleration is +2 or +2. With those units, oh, Jeremiah? Perfect. You could say 2 meters per second per second. If we're assuming these are like my truck from the previous example, each dot is a different snapshot taken 1 second later. We start at 2, 1 second later, we gain 2 meters per second. 1 second later, we gain 2 meters per second. So we could say it's accelerating 2 meters per second every single second. That's probably the most correct and straightforward way to say it, which is what we have here, 2 meters per second per second. That's a lot to write though, and like I've mentioned before, we scientists and really humans in general are kind of lazy, so we like to shorten things. So instead of saying 2 meters per second, we'll usually just say 2 meters per second squared. There's some math with that too that we'll go into in just a moment, but I see people writing stuff, so I'll give them a second. What's up?
So like in the equation percentage, since if you slow down, speed up, can you say like plus or minus x miles per second? So like you just slow down, or would it still be possible?
I think I know what you mean. I'm trying to picture it because I'm better with visuals. You're saying the equation would be what? Say it one more time. Plus or minus. So we won't actually end up with a plus or minus symbol in our equation. Like, have you guys done the quadratic formula yet? Okay, that one, there's a plus or minus baked into it. It's not going to be like that, but there is a piece of our acceleration equation that can be positive or it can be negative that we'll get to. We all set here? Okay. Then on to our actual equation. The mathematical definition for acceleration is just change in velocity over change in time. And we're introducing some new notation, some of my favorite notation, that being that funny little triangle. Which, speaking of, does anyone know what that funny little triangle means? Delta, change. Perfect, we got both of them. So first off, it's a Greek letter delta. So you will sometimes hear me say delta V, delta T. That's how you read that. But in math, that triangle, that delta, actually means change of whatever comes next. So we got change of velocity, change of time, or change in velocity, change in time. And as people are already writing, I guess I'll throw that up. We definitely have a new equation. Is definitely something I would put in my notes. So I'll give you another second while I jot down more points. People getting attacked with pencils. This will be a real exciting part of the video. Speaking of, I need to see. Is the whiteboard in there? It is not. Okay, good to know. As people finish up, we've introduced some new notation, this delta, but really we should have been using that delta already, but I didn't want to throw too much in at the very beginning of the year. But let's take our displacement that we have over here. Displacement is our final position minus the initial position. So that's a change. That's a change in position. So we could just write displacement is delta x, change in position. By the same token, we could write that velocity is delta x over delta t. Oftentimes when you see these equations written, or sometimes when we're working stuff out, even I will occasionally drop the delta on the time, because most of the time, when you're keeping track of time, you start your time at time is equal to 0. So then tracking the change of isn't quite as important, but technically you could start your stopwatch at 5 seconds, let it run to 10 seconds and stop there, and you'd have a change of time of 5 seconds. So realistically, we should keep it as delta t, but shorthand, that delta sometimes gets dropped, mostly on the t, but sometimes on other ones. We'll try to keep ourselves on top of things, using those correct notations when we can, because they are there for a reason. They're there to be as explicit and clear as possible. Questions about any of that? All right, and the last thing I'm going to do is expand this equation out just a little bit. I'll throw that up in the corner. We've got acceleration, delta v over delta t. So I could write that as acceleration. Change in v really means my final velocity minus my initial velocity. Change in time really means my final time minus my initial time. Just more often than not, initial time is 0, because that's generally when you start your clock. But these are saying the same thing. Usually we can get away with just keeping it like that, but sometimes we'll want to figure out one of these specific variables, so we might have to expand things out a little bit. The case where that happens the most would be when we're trying to predict the final velocity of something. Let's say I take that tennis ball and I want to drop it. And I want to know how fast it's going right as it hits the ground. So for that one, maybe I'd start like this. I'd start acceleration as final velocity minus initial. I'm going to leave my delta t as delta t, because in this experiment, I'm going to start my time at 0, so I don't really need to break these up and separate them. So I'll leave it like that for now. But I need to get an equation for final velocity, so I need to do some algebra. Multiply delta t up. That'll give me a delta t is equal to final minus initial. Then from there, we just add our initial velocity over, plus vi, giving us a delta t plus initial velocity is equal to final velocity. And the very last thing I'll do is I'm just going to flip this around, because personal preference, I like my singular variable to be on the left side. So I'm going to put final velocity over here. I need to know how fast I was going initially. and then I'll add my acceleration times time. This equation comes up so often that if I was taking notes, I would make sure I had that written down, just to save myself a little bit of algebra. But that is technically also the same as what we have up there. It's just rearranged, solved for a different variable. Questions there? All right. And I think we're getting kind of close to the end, although if my watch is correct, we still have a decent chunk of time. But that is all I have for us for now. So if we do have an extra chunk of time and my watch is correct, maybe make sure you don't need to turn anything in, or 3 minutes. Oh, I went slower than I thought. Then we'll stop there for sure.